Consider a ladder reaching a window. The wall is 12 feet high and the base is 5 feet from the wall. We use the Pythagorean Theorem to find the length of the ladder, c. Substituting our values, we get 5 squared plus 12 squared equals c squared. Calculating the squares gives us 25 plus 144, which equals 169. To solve for c, we need a new tool, the square root. We look for a value that, when multiplied by itself, results in 169. The square root is the mathematical inverse of squaring a number. If we square a value x to obtain a, then the square root of a returns us to x. For example, 5 squared equals 25. Therefore, the principal square root of 25 is defined as 5. It is crucial to note that the radical symbol represents the principal or non-negative root. While negative 5 squared is also 25, the square root of 25 specifically refers to positive 5. When we solve an algebraic equation, like x squared equals 25, we are looking for every number that satisfies the equality. Here, both positive 5 and negative 5 work, so we acknowledge both using the plus-minus symbol. By contrast, the radical symbol is a function. It is specifically defined to output only the principal or non-negative root. Therefore, the square root of 25 is strictly defined as positive 5. It is a common error to attach the plus-minus sign here, but the radical function does not allow for that. The symbol is a shorthand for the principal root only. Always remember, the radical symbol represents the principal, non-negative root. It does not imply both roots simultaneously. This distinction is vital for accurate algebraic work. Evaluating radicals is straightforward when identifying perfect squares. For the square root of 100, we seek the number that, when squared, equals 100. Similarly, the principal square root of 16 is 4. Because 4 times 4 is 16, the radical evaluates to 4. When evaluating expressions like the square root of 25 plus 144, the order of operations is critical. We must add the values inside the radical first. The product rule for radicals states that the square root of a product is equal to the product of the square roots of each factor. Mathematically, the square root of a times b is equal to the square root of a multiplied by the square root of b. This rule is incredibly powerful because it allows us to break down complex, large numbers into smaller, more manageable factors. By isolating perfect square factors, we can simplify radical expressions that would otherwise be difficult to evaluate. Consider the square root of 50. It is not a perfect square. However, we can use the product rule by factoring 50 into 25 times 2. Since 25 is a perfect square, we can split this into the square root of 25 times the square root of 2. This simplifies to 5 times the square root of 2. To simplify the radical square root of 300, we first look for perfect square factors within the radicand. We rewrite 300 as the product of 100 and 3, because 100 is a perfect square. Applying the product rule, we can separate this into the square root of 100 multiplied by the square root of 3. Since the square root of 100 is exactly 10, the expression simplifies to 10 square root 3. To simplify a radical containing variables, we treat the coefficient and each variable as separate factors. Let's break 162, a to the 5th, and b to the 4th into perfect square components. We identify the largest perfect squares for each. 81 is a perfect square, a to the 4th is a perfect square, and b to the 4th is a perfect square. Grouping the perfect squares together allows us to extract them from under the radical symbol efficiently. Taking the square root of the perfect squares leaves us with our final simplified expression, 9a squared b squared times the square root of 2a. The quotient rule for radicals states that the square root of a fraction is equal to the square root of the numerator divided by the square root of the denominator, provided that the denominator is not 0. This rule allows us to simplify fractions by handling the numerator and denominator separately. For instance, the square root of 16/25 becomes the square root of 16 divided by the square root of 25, which simplifies to 4/5. The quotient rule for radicals states that the square root of a fraction is equal to the square root of the numerator divided by the square root of the denominator. By applying this rule to the square root of 5/36, we can rewrite the expression as the square root of 5 divided by the square root of 36. Since the square root of 36 is 6, we can simplify the denominator. This leaves us with the square root of 5/6. This result is considered simplified because there are no longer any radical expressions present in the denominator. In algebra, we can only add like terms. 2x plus 3x simplifies to 5x, but 2x plus 3y remains unchanged because the variables are different. Radicals follow the same logic. The golden rule is radicals can only be added or subtracted if they have the same index and the same radicand. Here, 2 square root of 5 and 3 square root of 5 are like radicals, resulting in 5 square root of 5. However, 2 square root of 5 plus 3 square root of 2 cannot be combined. When subtracting, we treat the radical as a label. 8 root 7 minus 2 root 7 leaves us with 6 root 7. To add these radical expressions, we first observe that the radicands, 12 and 3, are different. We cannot combine them as they are. We simplify the square root of 12 by identifying its perfect square factor, 4. The square root of 4 is 2, leaving us with 2 times the square root of 3. Now, we substitute 2 times the square root of 3 back into our original expression. Multiplying 5 by 2 gives us 10. So we have 10 square root of 3 plus 2 square root of 3. Because the radicands are now identical, we simply add the coefficients. 10 plus 2 equals 12. Our final simplified result is 12 square root of 3. In algebra, we follow a standard convention for expressions involving radicals. We generally avoid leaving irrational numbers like square roots in the denominator. Standardizing the form makes it significantly easier to compare values and perform arithmetic operations like addition or subtraction, as the denominator becomes a simple integer. To achieve this, we multiply the fraction by 1. We choose a version of 1 that turns the denominator into a perfect square, specifically the radical itself divided by itself. When we multiply across, the numerator becomes the square root of 2 and the denominator becomes the square root of 4, which simplifies to 2. This is our rationalized form. The expression is now in standard mathematical form with a rational integer in the denominator. In algebra, we standardize fractions by rationalizing the denominator. Our goal is to eliminate the radical from the bottom of the fraction. We multiply the fraction by 1 using the radical itself. This effectively squares the denominator, turning it into a rational number. Since the square root of 2 times the square root of 2 equals 2, we arrive at our simplified rationalized result. When we encounter binomial denominators containing radicals, such as a plus b root c, we cannot simply multiply by the radical alone. To eliminate the radical, we use the conjugate. We simply change the sign between the terms. For a plus b root c, the conjugate is a minus b root c. This works because of the difference of squares identity. When we multiply these binomials, the middle terms cancel out exactly. This leaves us with the squares of the individual parts, successfully eliminating the radical. A conjugate is designed to eliminate radicals from binomial denominators. It works by exploiting the difference of squares pattern. When we multiply these binomials, the product follows the FOIL method. first, outer, inner, last. Notice the middle terms, negative AB root C and positive AB root C. These are identical with opposite signs, meaning they add to 0. This leaves us with a squared minus b squared times c. The radical is gone, successfully rationalizing the expression. In mathematics, there is a vital distinction between mechanical calculation and true conceptual fluency. By 2026, the focus has shifted from rote arithmetic to understanding the logic behind the rules. Calculation is the execution of a process. Fluency is the understanding of why that process works. Modern tools handle the heavy lifting, allowing us to master the underlying logic. Consider rationalizing a denominator. We don't just multiply by the radical, we use the conjugate to create a difference of squares. This logic applies far beyond just one problem. Using AI tutors or software to verify your work is an essential skill. Use these tools to confirm your results while using your mind to map out the strategy. True mathematical mastery in the modern age requires combining logical intuition with computational awareness. This is the new standard for success. Mathematics isn't just symbols on paper, it describes physical reality. Consider a ladder leaning against a wall. The length of this ladder is the hypotenuse of a right triangle. Using the Pythagorean Theorem, we find its length is the square root of the sum of the squares of the wall height and the distance from the base. If we move the base of the ladder, the values a and b change, and the radical expression calculates the exact new length of the ladder in real time. Dynamic software allows us to observe this relationship instantly, showing how radicals model continuous changes in geometric space. We often use the radical symbol to denote roots, but radicals are fundamentally linked to the laws of exponents. In fact, any radical can be rewritten as a power with a rational exponent. For instance, the square root of x is equivalent to x raised to the power of 1/2. This transition allows us to use standard exponent rules to simplify complex expressions. This definition extends to any root. The nth root of x is simply x raised to the power of 1 over n. By thinking in terms of exponents, we unify radical operations with the familiar rules of algebra. We conclude by reviewing essential practices. First, always distinguish between a radical expression and an algebraic equation. The radical symbol specifically requests the principal non-negative root. Equations like x squared equals 25 require both positive and negative solutions. Second, never distribute the radical across addition. Adding within the radicand must occur before evaluating the root. This is a common logical error that can be avoided by performing operations inside the symbol first. Finally, always standardize your expressions by rationalizing denominators. Remember that for binomials, multiplying by the conjugate creates a difference of squares, effectively removing the radical from the bottom of your fraction. Mastery of these concepts comes through systematic practice. Apply these rules consistently, and you will find that even the most complex radical expressions become manageable tools in your mathematical repertoire.